Okay, thanks. Yeah, and just to read it again, I'm Fred Calef. I'm from the Jet Propulsion Laboratory, and I'm the lead mapping specialist on Mars 2020, and I hold or held a similar position on various other rover and landing missions. Next slide, please. So we all know maps are important, but this article I read in Forbes really brought to the surface some of the things I knew subconsciously about why you would need a geospatial strategy, and really for any mission. So here I've crossed out company and put in mission, and key points being like every mission ultimately uses a geographic approach for decision making. We need to know where things are, where we're going, what we're going to do. And it's not just a single map, it's a framework of maps or data products. And then we use these maps to operate our missions. And the GIS system is a way to integrate all these dispersed data sets and from different systems, different formats, and put them into one collated location that everyone can use. Next slide. So NASA is into this transformed open science. Obviously, we want to continue to do this. We want to do this on the moon, and there are certainly the benefits of Y-TOPS, but I wanted to just put in a point that I think to achieve the goals of TOPS, we really need to have open science that begins with open software that we use for our operations using distributed data sets, open data sets. And who's it for? Yes, everyone, scientists, engineers on the mission teams, outside the mission teams, and the public. Next slide. So the problem that we all have, so many instruments, so much data, so little time. You have, the orbital data assets, which are obviously huge and numerous. You can use to create derived products like rock densities, elevation maps, slope maps, and traverse costs, and so on. And then you have landed data where you have specific point data and high resolution data sets. And, they come from fixed instruments, from mast cameras, from contact instruments. You can think of an astronaut as reaching out and putting an instrument on a rock. That's a contact science. So how do you put all that together? And then, of course, when you get a result back from a scientific instrument, you hear, that is an awesome result. Wow, look at all the silica. But where is it? It's always the second question people ask after they get a result. So how do we put all that together? Next slide. Oh, and just briefly, a little point, I want to make a, I had a thing that says time equals science. We want scientists to spend more time trying to do the science and less time trying to figure out the engineering aspects. How do I convert through 3 coordinate systems to get to one consolidated map, and how do I access the data? So one way we've addressed this with the current surface missions on Mars, the rovers specifically, is creating a web-based mapping interface. And it's open source. And basically, as a geologist personally, I want to see data in different views, your traditional 2D map view, but also in 3D, so I can look at stratigraphic and structural relationships, but also looking at the in situ data at the same time. And I can give you hundreds of gigabytes of data, but then if you have to organize it, that's a problem. So a web-based interface actually allows us to see all these different views at the same time and allows some interactive tools that you would normally not have access to or have the knowledge to use. Next slide. It's a little bit technical. The key part is you're not downloading software, you're not downloading data. You use the web browser as an interface, and then science and engineering and operation teams, who can be geochemists and rover planners and uplink leads, strategic planners, etc., project managers, the public, they can go to the interface, and then behind that, we have a web server, which then can use open source tools and products to serve the data to them or do certain processes. And importantly, we access open data sets, things that are more web friendly, like GeoJSON for vector data sets or TMS tiles for raster data. But we don't care where the data is. We don't have to hold all the data. We just need to be able to access all the data. Next slide. And the other important thing about open source is that your one mission doesn't have to build all the tools. So it's certainly the case for the tool we built, Multi-Mission Geographic Information Systems, this web-based mapping system that, it started with MSL, it can percolate all of its way down to Aegis or to Lunar Viper or to Cadre, these other CLIPS missions. And that's the way open source works. So you may need, let's say, 20 tools. Previous missions may have developed 15 tools. Now you only have to build to pay 5. And the next mission can build off the 5 tools you made so that you have this continuous range of development and capabilities that feed between missions. And also imagine if for someone who works on Viper, then goes to Cadre, or then goes to Artemis, they can kind of see how they know how these tools work, and they can know how to access data sets and have continuity in their skills. Next slide. Let's skip this one. It's just some software we developed for 3D. Next slide. So one of the things we've been doing is taking advantage of the open formats and expanding them a little bit. For example, in the lower right, we're showing basically like the hazardness of these test traverses that we wrote out, just so we can kind of take data sets, make it small, make it web accessible, but also increase the information there. Next slide. We can encode higher order data like elevation data, so that we can do things like viewing data in 3D as viewsheds or in elevation maps, or it could be even spectra. Next slide. And we've also enabled data, taking these formats, enabled them with time, so that we can scrub back through the mission and look at when things have occurred and when things have moved along or progressed. Next slide. Next slide. Okay. Yeah, so we make a lot of maps for the mission. So we go keep clicking through so that we have, your basic elevation maps, geologic maps, but target maps, that we use every day. And then we have things for like looking at samples, and the last one for strategic planning. Can we just go back 2 slides, 2 steps? It may or may not work. Yeah, right there. So importantly, you talk about tactical maps. So here's a tactical science operations map, which shows the locations of science observations, what instruments were used, and where they occurred, and then some context. So these are maps we make every day in a mission, so that the science team and people for the next gig keep track of what's going on. Next slide, please. Go ahead and click twice. Click one more time. So we've taken this web-based mapping system to then do geologic mapping, and so collaborative mapping within the science team. Click again, please. Okay, click one more time. So these are just 2 examples we've done for surface missions pre-landing. We did high resolution mapping at a scale of 1 to 5,000 in 1.2 by 1.2 kilometer quads. So people can do collaborative mapping together. They can look at other people's layers and see how they're seeing their units, and then solve the boundary problems. Not always, as you can see on this map. It worked so well, we actually ESA for the Rosalind Franklin rover did the same thing and did their collaborative mapping. And it's a way actually not only to make data, but also to build team cohesiveness, because you have the shared effort. Next slide, please. And then maps are going from static and really into dynamic, so that we can map data in real time. So you as a science team using can say, hey, I want to take a look at this area a little closer. I can map out a unit really quick. Okay. I can map out linear features and point features, and then I can assign FGDC, USGS official symbology to them. And I'll let it go. Just show here that we kind of have these already embedded. Give it your temporary name, but then maybe assign it an official feature. Okay, let's just click forward for time's sake. Okay, and again, we want data maps to be dynamic. So can you click? There's a video on this one. And so it's not just about seeing map layers, which we can have hundreds of them, but it's about creating view sheds on the fly, so you know where you're looking or where you can see. It's about doing line of sight analysis. It's about looking at other data sets that might be in 3D, like ground penetrating radar. It's about querying data sets. It's about overlaying data sets and showing them in 3D. All these things are useful for science operations, and various science and engineering team members make advantage of these tools. Next slide. And so CLIPS missions like Lunar Viper actually incorporating these web-based mapping schemes into their operational software, and we've actually modified it so it can do real-time analysis, and so they can display the data as it's coming up on the mission. Next slide. And as Matthew pointed out, yep, thank you. And as Matthew pointed out, that we are, MMJS was used as kind of a template to experiment with their Desert Rat, and later one of the jet exercises and expanding a little bit tools. There's a walkability tool that they built just to see how it works and start to get an idea of like, how do you transmit from science to flight. Next slide. Okay, that's it. I think I have one more slide, and that just briefly outlined some of the questions that they said we should answer. And so I just kind of put some information there. Okay, thanks.